Hello. Today let us start with this Wigner-Seitz cell. So you know Wigner-Seitz cell is a primitive lattice primitive cell, and it is constructed as follows. So we have different lattice points as shown in this figure. These there are other lattice points also in the surrounding. Okay, but we have just considered only these 9 lattice points. Surrounding there are many infinite number of lattice points. So let us take one lattice point in the center. In the center, now we wanted to construct a Wigner-Seitz cell around this lattice point. Okay, so for that we wanted to draw lines to connect all the nearby neighboring lattice points. So it will be like this. These lines, now we wanted to draw perpendicular bisectors. That means perpendicular lines. In this case, if it is three-dimensional, then there will be perpendicular planes. So we have to draw perpendicular planes to these lines. Then the volumes enclosed within these planes is called Wigner-Seitz cell. So this Wigner-Seitz cell contains only one lattice point. See, the center lattice point only. All other lattice points are outside. So a primitive. This is the definition of primitive cell. Primitive cell contain only one lattice point. Okay. Now you might have studied different crystal structures, but today I will discuss the cubic crystal structures once more. So there are 3 cubic crystals: simple cubic, then FCC, and BCC. So simple cubic lattice points are only in the 8 corners, and FCC, in addition to 8 corners, there will be lattice points in the face center also. Each face center, 6 face center, and BCC, in addition to the 8 corner lattice points, there will be a lattice point in the body center. So we can draw lattice. See, so if the lattice point contains only one atom, for example, let us take an example of one atom. Okay, one atom basis. Each lattice point is shared by 8 neighbors. The contribution of the cell is 1 by 8. Okay, so 1 by 8 into 1 by 8 part of the lattice point is for this cell. So the 1 by 8 into 8 corners, 1 lattice point. Okay, so let us draw the atom. Okay, so this will be the shape of a simple cubic structure. So from the figure you can see that the side is A, and this will be radius of an atom. So A is equal to 2R. From this you can find out the volume of the lattice cell, that is A cube. Total volume of the atoms in the unit cell is V is equal to 4 by 3 pi R cube into number of atoms. It is only one atom in the unit cell. So therefore 4 by 3 pi R cube. So using this, and the packing fraction is equal to V divided by capital V is about 0.52. If you substitute, it will be 0.52, that is 52%. Okay, so you substitute the value of R and A from this thing, then R is equal to, here R is equal to A divided by 2. This is the simple cubic. For a FCC, for FCC, for an FCC, the unit cell looks like this. Here, this is the side A of the cubic cell. This radius R. Therefore, we can write the relation between the radius and the side is for R is equal to root 2 times A. So therefore, R is equal to A by number of atoms in the cell is equal to 8 corner atoms. So 1 by 8 into 8 plus, there are 6 face center atom. So each face center atom is shared by the 2 lattice cells. That is 1 by 2 into 6. So therefore it will be total number of atoms is equal to 4. Therefore volume of atoms in the unit cell V is equal to 4 by 3 pi r cube into 4, which is equal to 4 by 3 pi r is a by 2 root 2 whole cube in 4. So this is equal to, on simplifying we get pi a cube divided by 3 root 2. Okay, and V is equal to, the volume of the unit cell is a cube. So the packing fraction is equal to pi a cube by 3 root 2 divided by a cube. So equal to pi by 3 root 2 is equal to 0.74. Okay, so the fraction of the volume occupied by atom is equal to 0.74, that is 74%. Okay, so the remaining 26% is the void space. Next is BCC, body centered cubic crystal. Okay, BCC. So in BCC, in addition to the corner atoms, there will be, or corner lattice points, there will be one lattice point in the body center. Here, the body diagonal of the unit cell root 3 times A is equal to 4R. Okay, for R is equal to root 3 by 4A. Now, number of atoms in the unit cell is equal to 1 by 8 into 8 plus a body center atom. So this is equal to 2. Okay. Therefore, volume of atoms in the unit cell V equal to 4 by 3 pi r cube into 2, which is equal to 4 by 3 pi r is root 3 by 4 a whole cube into 2, which is equal to root 3 divided by 8 pi a cube. Okay. Now the volume of the unit cell is equal to a cube. Therefore, packing fraction of BCC is root 3 by 8 pi. Okay. So this is equal to 0.68. That means 68% is the volume occupied by the actual volume occupied by atom. Okay. Closest packing of all these three cubic crystals is in FCC, face-centered cubic crystal, the primitive cell of a body-centered cubic crystal. So the body-centered cubic lattice contain 2 lattice points. That means it is not a primitive cell. But the simple cubic cell is a primitive cell because it contains only 1 lattice point. And the FCC contains 4 lattice points. Okay. So we wanted to see what is the primitive lattice of a body-centered cubic lattice. So here in this figure, the primitive lattice is shown in this. The white edged cube is the body-centered cubic lattice, and the black one is primitive lattice. And the body-centered cube, this is the body-centered atom or body-centered lattice point in the BCC. This point is the lattice point in the body center of the next cell, and this is the lattice point, the body centered lattice point at the right of the unit cell, and this is the lattice point in the top of the unit cell, and the remaining are the corner. So the primitive cell of a BCC structure is a rhombohedron because the angle between the two sides is 109 degree 28 minute. Okay. And the length of one side of the primitive cell is actually the body diagonal, half the body diagonal of the BCC. Okay. So it is half the body diagonal. That means 1 by 2 into 3 root 3a. Now let us see the primitive lattice vectors of BCC. Okay. For that, let us consider this BCC structure here. So this point, this lattice point can be considered at the origin. Okay. So there are three basic lattice points, 1, and here lattice point 2 and 3. So these vectors, the corresponding vectors as a1, a2 and a3. So this is shown in this second figure. So vector a1 and vector a2, vector a3. Now the sides of this unit cell is BCC cell is A. We know this is cubic. All the sides are A, and therefore this small vector a1 is the primitive lattice vector. So if we consider the parallel to our the parallel sides, and the volume enclosed will be the primitive cell. Okay, so here a1, a2 and a3, and consider parallel vectors to these vectors, and consider volume enclosing this, and this will be the primitive cell. And the vector a1 is, what is vector a1 is equal to, so this is along positive axis a by 2, and along positive y axis a by 2, and along negative z axis a by 2. Therefore a divided by 2 x vector x cap plus y cap minus z cap. So this is the primitive lattice vector of BCC, first one. And second one is z axis plus a by 2, y axis plus a by 2, and x axis it is negative x axis minus a by 2. So therefore a by 2 divided into minus x cap plus y cap plus z cap. Similarly a3 vector is, so a by 2 x minus y plus z cap. So these are the primitive lattice vectors. Okay. Now let us consider the translation vector, primitive lattice vectors of FCC. Okay. So for that, so here this is the FCC lattice cell. We can consider this corner atom or corner lattice point is at the origin. And so there is a face-centered lattice point, and here one more lattice point in the next face, and there is the third lattice point. Okay, here. So these as the corresponding vectors a1, a2, a3 are the primitive vectors. And now we can imagine parallel vectors to these three vectors, and consider a volume enclosing all these vectors. Okay, so this is the primitive lattice. So the primitive lattice vectors are a1, a2, a3 is given by, so what is a1? So if this is origin, the side of FCC cell is A. Therefore, to the face center, the vector from origin to the face center is a1 is equal to a by 2 x plus y. So this is the vector 1. Similarly, a2 is equal to, a2 is the to this face center, okay, vector to this face center from the origin. So y plus z. So a by 2 y plus z, and a3 is equal to a by 2 z plus x. Okay. So these are the three translation vectors, that is primitive translation vectors of FCC.
Okay, so this is also a rhombohedral primitive cell. So these lattice vectors are given by this equation. The angle between them is, each of them is 60 degree. Okay, here x, y, z are the Cartesian unit vectors. In a simple cubic, the simple cubic itself is a primitive cell. Therefore, vector a1 of simple cubic is equal to vector a times x, and a2 vector a2 is equal to a times vector y, and a3 is equal to a times z. Okay, because simple cubic itself is a lattice primitive cell, because in simple cubic there is only one lattice point, but in FCC there are 4 lattice points, and in BCC there are 2 lattice points. Therefore, we have to consider a separate primitive cell for these 2 cells. So see, in the case of FCC, we have, if you see this primitive lattice, there are 8 lattice points in the corner. There is no other lattice points. So therefore, the lattice points per primitive cell is equal to 1. Okay. So that is the definition of primitive cell. We will continue in the next class. Thank you.